Good afternoon. My name is Paul Wright. I'm the director of CITRIS, this lovely building here. I feel very lucky to be in that situation. This is also being webcast, as you know. It's going out to our other campuses in Merced, UC Santa Cruz, and UC Davis. The sandwich that you're now eating is sponsored by the Infineon company. A couple of years ago, I made a pathetic joke that there's a piece of smart dust in there made by Infineon that's going to track you forever. But I'd also like to invite you to some other events that we're having. Every Friday, we have another luncheon called the I4 Energy Luncheon. So please join us for those luncheons every Friday. On the 28th, which is a week on Thursday, there's a meeting here which is the post-Copenhagen discussion where several faculty from the Goldman School of Public Policy and from economics and sociology will be talking about the Copenhagen meeting and what the prospects are for a accord around reduced carbon footprints. And then on the 29th, I really hope you would come to a ribbon cutting that we're having for our I4 Energy activity. There'll be a discussion in here and some talks by distinguished folks like Arthur Rosenfeld, who was the California Energy Commission, who just stepped down, out of Berkeley, faculty member, a very distinguished physicist. And then we're going to go upstairs for a ribbon cutting of the energy center that we have on the fourth floor. Another fundraising opportunity, mostly for students that I see out here, is that there are $30,000 prizes available through CITRIS for our big ideas competition. One of our most famous winners of that is the cell scope project that you may know, where a microscope is attached to a cell phone and a blood sample of somebody with tuberculosis can be seen on the cell phone by a doctor, or the cell phone can send it to a central database at UC Davis. Today, it's a great pleasure to introduce someone who I've become extremely fond of and respectful of over the last 2 or 3 years, because a large number of ECS faculty are now working on this area of low-cost electronics from an energy perspective. There are a number of new projects that are being funded in this area, and Professor Yablonovitch is the leader of that work and is also involved in our I4 Energy activity. He has a very distinguished academic background, having come from Harvard University, a university you've probably heard of in the past. He has a degree in applied physics from there. He worked at Bell Labs. He's worked at Exxon. He's joined the Bell Communications Group in solid-state physics. And then in the early 90s, he joined the faculty at the University of California, Los Angeles. And then more recently, in the last 3 years, we've had the great pleasure of having his leadership and his wonderful research work on the campus of the University of California, Berkeley. So even though you're eating and you have a sandwich on your hand, please join me in the usual way with a warm round of applause for
Paul, thank you very much. Excellent. Okay, I'd like to thank everyone for coming out on such a rainy day. I think the fact that it was rainy means we have the real serious Berkeley people here. And the people who are just sort of can't decide where to go in the Bay Area, they didn't make it this morning. It's just as well. So it's a somewhat interesting topic. Let me turn my little marker on here. And this is searching for the millivolt switch. It's loaded with questions because I think somebody in the front row asked me, okay, am I going to find out what is the millivolt switch? And, well, we'll find out some options. We don't actually have a winner yet. And so that'll be kind of interesting to find out. So let me motivate things a little bit, talking about the worldwide use of energy for information processing. Information processing has become a very, very big thing in my lifetime. And I think back to when I was in graduate school, it was a very tiny thing back then. And now it's a very big thing. And it looks poised to continue to grow. So for example, whenever we're interacting with our computers, we're often downloading from data centers. And everything having to do with information technology is growing at a breakneck pace. And In fact, isn't that what the IT in CITRIS? Someone has to correct me. I think the IT in CITRIS might stand for information technology, but it gives you an idea of the energy usage in 2000. This is not for all your electronic stuff. This is just for the data centers. And you can see very typically it grew by a factor 2. And these things tend to grow very much. And the amount used is actually very large. So we will calibrate this in a minute. How much is billions of kilowatt hours per year? We'll soon get some perspective on it. But here's one perspective. If you took the world's data centers, just the electricity used in data centers, it represents a medium-sized country, somewhat maybe rivaling the size of Mexico. And this data is all back in 2005, so I'm sure it has surpassed the energy use in Mexico already. So this is an important thing to keep in mind about information technology. It's growing. It is always growing. It will continue to grow. But it's getting to a point now where there's going to be some issues regarding the energy use. And this is a picture of all electricity used in buildings, and you can see that the electronics is a pretty significant fraction right in the middle of that. And of course, part of this data, where did I get this data, is that we're very lucky to be down the hill from LBL, where they have studied this in great detail. And they're sort of envisioning what's going to happen. So if you scale it as a fraction of the GDP of the world, you end up with, of course, GDP grows because we have many developing economies and they're growing. And at the same time, electronics is growing faster, and semiconductors are even growing faster. And so we see that eventually the use of electricity for information processing will eventually become very, very large. And we have to sort of anticipate that. And does that mean that we will maybe compromise and have less information technology? I doubt that. I think what we'll do is we'll become more efficient. And so that's what this talk is about. So that's the motivational part. And usually at these talks there are a few policy wonks. And in the question period, don't run out because I'm going to ask the policy wonks some questions, just because I'm going to do it in reverse. Okay, so but the main part of the talk is scientific and technical. And so actually, let me ask the question right now. So we're getting into the technical solutions. Suppose we solve this problem, and you'll see in a minute that there's a lot of improvement possible. Maybe 6 orders of magnitude of energy efficiency improvement might be possible in information technology. And suppose we became like super efficient that way. Does that mean that the amount of energy used will actually be less or will it actually be greater? Okay, because usually when we make things very inexpensive, people want more and more of it. And this has been the case with information technology. So that's the riddle for the policy wonks. And I'm just giving you some time to think it over. And maybe by the question period you'll have an answer for that. Because I don't know for certain. Okay, so that's sort of the policy part. Let's go to the technical part. So I'm going to ask how much energy does it take to process a bit of information? That's the fundamental act of information technologies. You do something with a bit of information. For example, what would be the cost of reading out your flash memory? So there's a little flash memory stick, and well, what happens? In the flash memory, there are many little transistors that are held on or off by static electricity. That's why it doesn't go away. The static electricity is held inside some silicon dioxide, which is a good insulator. So the static electricity stays, and the transistors are either on or off. Now, how can you tell? Well, you just measure the resistance. If a transistor has a low resistance, that means it's on. So reading out the flash memory is kind of like running an ohmmeter. Okay, and an ohmmeter will tell you which transistors are on and which transistors are off. So let's ask how much energy does it take to operate an ohmmeter? Now, an ohmmeter is rather different from like a voltmeter or an ammeter, because a voltmeter, you attach the voltage probes and you get the power to turn it on. The power is actually coming from the circuit. And same with an ammeter. There's current, so the current can drive the ammeter. But an ohmmeter is different because you have to supply voltage and current in order to read out the resistor. So let's ask what is the energy cost of reading a resistor, finding out whether it's on or off. And this is like a prototype for measuring 1 bit of a flash memory. Okay, so you want to do it very carefully. You fight with noise. Of course, it's somewhat of a disappointment to me that electrical engineers don't automatically learn about analog noise anymore. But these are the equations. There are 2 types of analog noise. One of them is due to the graininess of the electrons. That's called shot noise. And the other is Johnson noise. This is due to thermal fluctuations, just like you have in chemistry. And they both give little bits of current noise. Now, so before I give you the answer and go through, this is the one slide with some equations. I apologize for it, but I will set up a little riddle ahead of time. So I asked this question: what is the right strategy to read out a resistor, read an ohmmeter, and use the least amount of energy possible? So I have 2 graduate students, and one graduate student says, oh, I know what you should do. Just do everything very slowly, very carefully. Don't use any excess current, and be very, very careful in the measurement. And then you'll use as little energy as possible. And the other graduate student says, no. Just do it quickly. Get it over with. Use what you have to use, and then you don't use any more energy at all. Okay? So let's set it up as a riddle, as a puzzle, and let's figure out which of the 2 graduate students is correct. So, of course, I have to go through this a little bit more carefully. I have these 2 noise sources, and I ask then, okay, well, you look at the strategy for doing this. It's generally smart for the shot noise to overwhelm the Johnson noise. And that occurs when you see the 2 equations are rather similar. And the main difference is there's current in here and there's KT here. So anyway, it ends up that in order to have the shot noise be dominant, you should apply a voltage of at least 50 millivolts. So that's sort of the first recipe. You don't want to have to fight the Johnson noise. So put on enough voltage that you don't have to deal with Johnson noise. So it says run the ohmmeter at 50 millivolts. Okay, that's fine. And then the second requirement is that we need a decent signal-to-noise ratio. So the signal is the current going through the resistor. The noise is the shot noise. This is the noise that's associated with discreteness of charge. Today is a good example for doing this. This is the noise when the raindrops are falling on your roof, and you hear a lot of noise hitting it because it's all made up of discrete impulses as each raindrop hits the roof, and so you get this. So very similar with current in a wire is the individual electrons are sort of grainy, and so you get some noise associated with it. And the first thing you notice, well, you can combine these 2 square roots, bring the square root up here, and then this current has to be larger than that current. This current is kind of an interesting current. It represents 2 electrons per unit bandwidth. Okay, that's not surprising. In order to read anything within that unit of bandwidth, you better have at least some electrons to read. Okay, so we're in good shape. We know what voltage we need. This is the voltage. We know what current we need, and the power required is the voltage times the current, and we get a certain answer. And notice that the answer, it's kind of a simple answer. Its power is 4 kT, so this is some kind of thermal energy times the bandwidth. And that's the answer. Okay, now which graduate student was right? Should you go very slow or should you go very fast? And the answer is they're both right. It didn't really matter. Okay, and the reason is that it's 4 kT per bit of information. If you go very slow, you have a very narrow bandwidth. Per bit, it's still 4 kT. If you go very fast, you have a very broad bandwidth, so delta F is bigger, but it's still 4 kT per bit of information. So this is kind of a universal law. This is sort of well known for a very, very long time, and it's sometimes associated with a name of Rolf Landauer, who was a very famous and brilliant theorist who worked at IBM. Now, that's, of course, with not much of a signal-to-noise margin, so let's throw in a factor 10. Now we have a decent signal-to-noise margin, and we'll say that to read out flash memory costs 40 kT per bit processed. Now, maybe some of you are not familiar with that unit of energy, and so unless you're a physicist, you might not be familiar with that. So I just realized, so I've converted it to different kinds of units, and I left off the chemist, so I'm going to put in the chemist toward the end. So what does it mean that it takes 40 kT to process 1 bit of information? So let's convert it to joules. Well, maybe this won't help either. 0.16 attojoules. Well, maybe you're not perfectly calibrated in attojoules. An attojoule is 10 minus 18 joules. So maybe that's not your cup of tea. Well, what if you're a communications guy? So the communications guys, they send information at, let's say, a gigabit per second. Say, how many microwatts does that take? Well, actually, when they do it in milliwatts, because that's what it really takes. But this limit of 40 kT is in microwatts, very tiny amounts. And in fact, if you look at all these things, it's 1,000,000 times less energy than we are consuming today. And you'll see why in a minute, why we're so inefficient. Why are we using 1,000,000 times more than we need to? That's kind of shocking. Now, I just realized I had not included the chemists, and I believe, if my memory serves me, this is 22 kilocalories per bit of information. No, not per bit, per mole bit. So it's times per 6 times 10 to the 23 per bit. Okay, I have to save it up. Next time, if I give this talk in a chemistry department, I'll give it in kilocalories also. Okay, moving on. So, okay, what's the deal? With all the different technology options, can't we be efficient? Well, let's try to decide if we can be efficient. Let's talk about certain functions, like memory. Okay, and the function I just gave was reading out flash memory. But in general, there's many kinds of memories. Just flash memory is just one kind. There's many kinds. There's static RAMs and dynamic RAMs and magnetic spin and little nanoelectrochemical cells and memristors and nanomechanical gadgets and molecular gadgets and glasses which have phase change and maybe carbon nanotubes and so forth. So there are a great many ways to do memory. And in fact, the people who do memory, so memory and storage are somewhat synonymous, the people who do memory, they say that they're getting there. They're getting pretty close, especially the disk drive people. They're getting there. They're pretty close. But why is this doing so well? There are so many options. And some of them are more efficient than others, and some of them can be very, very efficient. There are a great many ways to do memory. There also, might surprise you, there are actually quite a few ways also to do logic. And it looks like technology is on a trajectory to do very well, to make these functions very, very efficient. You have a great many options, and with so many options, and there's a similar number of options for logic, with so many options, we're bound to do reasonably well. But what about communication? Communication is an important information technology function. And do we have a great many ways to communicate? And so, well, we have a little problem. When you communicate in information processing, latency is very, very important. And so because of latency, we probably want to communicate at the speed of light. I mean, there are very strong reasons for communicating very, very quickly. So, well, what goes at the speed of light? Well, microwaves. Well, what's microwaves? If you buy a 2 gigahertz processor, 2 gigahertz is microwaves. This is very high frequency. It is electrical, but it's AC, and it definitely moves at the speed of light, like most electricity, and also optical. We have optical communications, and that also runs at the speed of light. And once we mention these two options, we very quickly run out of communications options. And so what you're going to see on the next slide is that, yes, we can probably eventually get down to really good efficiency with storage and with logic. But with communications, we are inefficient, and we seem destined to remain inefficient. And the reason is that, well, we're boxed in with communications. We don't really have that many technical options because we want to run at the speed of light. So if you ask what is on a chip, I have here a picture of a chip. And you say, well, what's going on? It's all wires. You know, just look closely at this. It's really all wires. And so this is a little cartoon. This is a cross-section of a microchip, and you say, well, where are the transistors? The transistors are these tiny things down here. The whole rest of it is wires. And this is sort of a tip-off that communications in information processing is very important. If you look at this, there are 9 layers of communications, and just the bottom layer is transistors. So it tells you how important communications is in information processing. It's, of course, the other things are important too, but the other things are on a trajectory to become very efficient. So let's ask, what is the energy cost for electrical communication? And here I will, again, this is actually Johnson noise again, so put in Mr. Johnson. This is due to thermal fluctuations. This is actually the voltage, the noise voltage you get from a resistor. Depends upon the bandwidth and or number of bits, and depends upon thermal energy KT. Now I can take the resistor, bring it downstairs. Now I've got V squared over R, and if you've taken any even physics classes, you should recognize V squared over R is power. It's actually called the noise power. And it's the expected noise power on a wire, and, well, it's not bad. It's, we're back down to 4 kT per bit again. And so what's the big deal? Communication over wires should be very, very efficient. What's the problem? Why is there still a problem? So let me try to indicate this by asking what is the natural voltage range for wires. And so there's actually a physics to wires. It's kind of interesting. This is sort of people who think about chip scaling, they kind of know all this. So let me introduce, this is like very simple stuff. This is freshman physics stuff, I hope. And you have resistance. Now, one of the things you learn about resistance, you have resistivity, and this is length over the area of the wire. So the wire is A, so the area is A squared. Okay, so it's length over area. So that's the resistance of a wire. Okay. Now we ask, what is the capacitance of a wire? So if I ask you the capacitance of a wire, you say, well, you haven't given me enough information. I need more information. True, the wire by itself, you need to know what the counter electrode is and so forth. But I'm going to give you now a quick way of estimating the capacitance of anything. A human being, you can estimate the capacitance of a human being this way too. And that is that capacitance scales with length. Okay, if you have a long wire, you have more capacitance. It's kind of it does scale with length. This is a very good approximation to the capacitance of a wire. Yes, don't I have to say where the counter electrode is? Well, take it to infinity. It's not affected much by where the counter electrode is. Strictly speaking, or technically, it's a small logarithmic correction where the counter electrode is. So this is a pretty good way of estimating the capacitance of wires. So one of the things that we learn in electrical engineering is that there's a speed limit. It's called the RC time, resistance times capacitance. So I simply multiply these two things together. And now the L's, the lengths get squared, and the area already had a square in it. Okay, so it's length over width all squared is the RC time of a wire. It's sort of like a speed limit for wires. And let's say, now everything I've done now is more or less fundamental constants. You look at resistivity, copper is just about close to the best resistivity. You can't really do much about the dielectric constant. It's just there. There's no leverage on that. So everything is like fundamental constants, except what is the goal for the RC time? This is more of a sociological constant or a business constant. And it has to do, what is the speed at which you would be interested? And broadly speaking, it represents the clock speed of computers. But that's not a fundamental constant. That's just a business reality. So let's just put it to the clock speed. Nobody's interested in a clock speed a lot less than 10 gigabits. So I'm just going to put in 10 gigabits. But other than that one sociological factor, everything else is pretty much fundamental constants. And what it says is that the longest wires, then I can solve for L over A. L over A is the aspect ratio of the wire. And I can solve for what is the maximum aspect ratio of a feasible wire for wired communication. And thankfully, it's reasonably long. It's about 5,000. A wire is still functional if it's 5,000 times longer than its width. It's functional at this particular speed. And this is good because you can just have these long wires. Then you have a repeater. The repeater has transistors. On chips, the transistors are practically free, so you can just do this. And you can actually communicate quite a long distance. And if you have a long distance link on a chip, this is typically how they do it. But what we've learned is that there is a certain aspect ratio to expect. Okay, so there's my aspect ratio. Don't round it off to 5,000. Don't worry about the 4,800. Okay, now once I have an aspect ratio, I can make an estimate of the resistance of those wires. Now, first of all, I have the aspect ratio, so that part is 5,000. I have one more piece of information, and that's one more dimension. It's the minimum dimension of the wires. And the minimum dimension, it's another one of these, it's not a fundamental constant, but it's a sociological constant. Very famously in chips, that gets smaller with each generation. And right now we're working on the 45 nanometer generation. So let me put that in. It changes slowly. It changes every few years. So what it tells us is that the typical wire has a resistance of about 2,000 ohms. And we can also estimate the same way the capacitance. And a typical long wire has a capacitance of 7 femtofarads. So from these two pieces of information, we can answer the fundamental science question, what is the voltage that the wire would be happy with? So I calculate once again the Johnson noise, and well, it's down around half a millivolt. So what it tells you, as long as you're operating at a few millivolts, the wires are kind of happy. They have decent signal-to-noise ratio. And also, you should maybe work at a few microamps of current. So you now know what wires like. They like a few millivolts and a few microamps, and then they're happy, and they have a decent signal-to-noise ratio. Now, maybe you didn't follow this exact derivation, but I'll give you one other example that you may have experienced if you took a lab class. And if you had an oscilloscope. So the oscilloscope has many, many scales on it. And you look at the oscilloscope, it's just a line, okay? But then if you go to the most sensitive scale on the oscilloscope, the line gets noisy, and noise comes in. And if you remember, if your memory serves you, what happens? Yeah, once you go down to the 1 millivolt scale, it gets pretty noisy. And most oscilloscopes, then they stop at a millivolt for this reason. So I'm just telling you something you might have already known, is that wires only get noisy down around a millivolt, and not surprisingly, when people talk about noise, they usually talk about microvolts. It'll be in this case, would have been 560 microvolts. So that's kind of interesting. This is not that big a deal. It just says that you need a few millivolts for the wire to do reasonably well. And so what's the problem? It looks like it's going to be quite efficient. We're down near the theoretical limits. So here is the problem. I've gone through very carefully with the Johnson noise and so forth, and I concluded that the wires would be happy at a few millivolts. Let's ask at what voltage the transistors would be happy, because wires are not enough. You have to have transistors. So we said, well, what is the natural voltage range for a transistor? Well, a transistor, and I hate to use this sort of technical language, but a transistor there's an energy barrier. And then to turn the transistor on, you lower the energy barrier, and current goes over the energy barrier. And so the technical term for that is a thermally activated switch. So even if the energy barrier is high, a few thermally excited electrons might jump over. And so transistors are always fighting that. And so in order to defeat that, the natural voltage range of transistors is some significant multiple of this thermal voltage. So this thermal voltage it can be expressed as an energy, but it can also, as an energy, it's attojoules. But as a voltage, it's 25 millivolts, but and that appears as a Boltzmann probability, and the transistors are run on Boltzmann probability. But if you really want to have a good on-off ratio of a transistor, you have to run at many, many factors of kT. So let me remind you, the Boltzmann factor is e to the minus, let's say, QV over KT. So it's just like in chemistry and material science. This is very, very similar. And then we say, well, we want to have a good on-off ratio, so this should be around 10 to the 6th on-off ratio of 1,000,000, and it rapidly requires you to use a voltage which is much greater than this KT over Q, which is around 25 millivolts, and so by much greater, you're up around somewhere between a half a volt and 1 volt. So the transistors really want a pretty high voltage in order to have a good on-off ratio. Okay? So here is the discrepancy, and here is the cause of the problem. And let me erase some of this math here. There is what I state is that there is a voltage matching issue. The transistors being thermally activated, they have to run way above 25 millivolts. In fact, they have to run close to a volt or half a volt at least. So the transistors want to run at a high voltage. The wires want to run at a low voltage. Okay? Now, let's say, well, instead of voltage, let's talk about energy. So a transistor, the energy requirement is always around this much, which is 1 electron volt. So a transistor, maybe it could operate with one electric charge at 1 volt, and that would be the right amount of energy. But the wires, they seem to want 1,000 electrons at 1 millivolt each. So the energy usage is the same in both cases, but in one case you're operating at a low voltage, in the other case you're operating at a high voltage. Now, let's say, as we do today, we ignore this. We just ignore this. So we end up operating at close to a volt when the wires would be happy, let's say, at a millivolt. So we're running with way too good a signal-to-noise ratio. And this is quite common. But it's not just the voltage ratio, it's the voltage ratio squared, because power goes as voltage squared. And so we end up being inefficient by a factor of 1,000,000. And, in effect, we have over-designed all of our logic circuits. They're running at much too high a signal-to-noise ratio, and they're being wasteful. And they're being wasteful by a lot, by about a factor of 1,000,000. And this is essentially where we are today. So if you look at information processing today, almost every function is 1,000,000 times less efficient than it should be. And it's derived from this idea that we're using too much voltage. So you think about this and say, oh, is this something new? And so no, actually, this was already figured out by Gordon Moore. Okay, Gordon Moore is famous, Moore's law. He said everything is going to miniaturize. But he said something else that is overlooked. And I have here taken right out of his 1965 paper where he predicted Moore's law. He also said, and I'm going to call this Moore's second law, he says power is needed primarily to drive the various wires and capacitances associated with the system. And he said as miniaturization occurs, the wires get shorter, there's less capacitance, and you become more energy efficient. So Moore, in addition to predicting miniaturization, also predicted that everything is going to be more energy efficient. And it has happened. Everything has become more energy efficient. Here is Moore's law for critical dimension. This is Moore's first law. It says everything gets smaller. Yes, 50 years ago it was maybe 25 microns in size, each transistor, and now we're at the 45 nanometer level. So we're about here. So things have really improved over the past 50 years. I love these log scales with year. Here, look, this is an entire decade, a lifetime, 1960 to 2060. It's quite amazing. He predicted miniaturization, but he also predicted that there would be more energy efficiency. And there is. We are more energy efficient than we used to be because the wires have become shorter. And that has also improved. It's actually improved at a tremendous rate. But we run into a problem. We run into a gap. It was only so far that we can go. So we're about here. The transistors are actually quite efficient by themselves, but when you include the wires, it gets to be quite inefficient. And we're over here. We're around 1,000,000 KT for processing a single bit of information. And I think we're going to have to go beyond merely making the wires shorter. We're also going to have to lower the voltage. And so that becomes then the big question. So that's the question mark in the title of this talk is, okay, is there a device, is there a switching device that can operate at millivolts instead of the transistor, which operates close to a volt? And so I have here on this slide a montage of the different technologies that have been suggested to have a switch to replace the transistor, but that would operate at a much lower voltage. So let me tell you the plan for the remainder of the talk. And the plan is I'm going to outline some of these proposals that people put forth. They all have problems, because if they didn't have problems, we wouldn't need 7 different ones to put on the slide. And I'll say, okay, what the idea is, why it's not quite there yet. And then the challenge will be for the students in this audience is that your generation is going to solve this problem. I have here some proposed solutions, but the actual solution will come probably from a smart young person who sees a little further than other people have seen and ends up developing the right technology. We need a switch that operates at a much lower voltage. Let's see how people plan to do it. So let me explain the montage. This says transistors. Well, aren't transistors not good enough? Don't they require high voltage? Yes, but we can sort of modify the transistor. We can invent new types of transistors that might overcome this problem. And it's sometimes expressed as steeper subthreshold slope. This is it turns on more rapidly. It's in effect a more sensitive transistor. It can switch on and off, let's say, with millivolts, whereas conventional transistors, maybe you need at least half a volt to switch them on and off. So the transistor can improve. Okay, so that's one option. Another option that people have put forward is that, oh, all you wire guys, you're missing it all because it should really be optical. And so they suggest that it should be done by optical communication. And gives you an idea why this works is you might have a photodetector, you might have a single photon coming in, and even if you have a single photon coming in, you'll still produce a volt. And so it's kind of like a weak signal still produces a big voltage. And that would maybe match the voltage requirements of transistors. So that's an idea that a lot of people believe in. Here's another one. This is being actively researched. There is a lot of federal funding for it. And it says, well, wait a minute. I'm having this problem. Why don't I just lower the temperature, do it cryogenically? And so I didn't mean to erase that. Put a line underneath. Oops, it's in a bad spot. We'll get to it later. It's basically KT. And let's say you lower the temperature of operation of the circuit. Obviously, the voltages will go down as well if they're related to KT. But then the wise guy comes along and says, yeah, sure, you're using less energy, but then you have to pay for the refrigeration. And it might be a wash. But it turns out if you analyze it very carefully, it's not a wash. You still win by going cold. And so that's worth thinking about. You could think maybe if someone could invent a nanotransformer, maybe we'll have the wires would operate at 1 millivolt, and then we have a nanotransformer, and that goes to 1 volt, and we can continue using regular transistors. We just have nanotransformers wherever we have a communications wire. Okay, it's an idea. Here's another possible solution. This is taken seriously. Quite a few people are working on it. Is that instead of an electrical switch, let's have a mechanical switch. And a mechanical switch, surprisingly, might be as little as 10 millivolts required to switch a mechanical switch. And so it's kind of interesting. Here's one. This is sort of like a symbolic way of writing it, but it represents what's called a magnetoresistive switch. You actually have these in every hard disk because they are resistors that sense magnetic field, and this is how you sense the bits of information on your hard disk. Now, about 20 years ago, people discovered that they could have a resistance change as much as a few percent, let's say 5%. They said, 5% change in resistance. Let's give it a name. Let's call it giant magnetoresistance. Okay? And those guys went on, 2 years ago they won the Nobel Prize, and part of the reason, this is in everybody's hard disk, so you can't argue with it. because everybody's using it. But there was, over the past 20 years, this has improved greatly. And what used to be a 5% change, and they call it giant magnetoresistance, now they have a 500% change in resistance. And it's starting to look more like a switch, more like a real switch. And so with a 500% change, it went through various verbal reincarnations. It went from giant to colossal. It became colossal magnetoresistance. But, okay, it's not a transistor with an on-off ratio of 1 million, but it's amazing they now have an on-off ratio of 5, so it might possibly have some use. People are looking at it. It's improved a lot. Maybe they'll eventually get to a high on-off ratio. And that would be kind of an interesting switch. And it operates on current rather than voltage, so it's low voltage, high current, better match to the wires. And then I have the final one. This is not an exhaustive montage. There are other things out there. And so you can think about, what if you had, like the ultimate switch, you have 2 copper wires very close together, and they're almost touching, but then you electroplate a little tiny bit of copper. I mean, how many copper atoms would you have to electroplate across to cause a short circuit? That's a switch. And that is actually also being very intensively investigated. So let's see how much time I have. I have just a little bit of time to go over some of these options, so I'll just go over them. What about a transistor? Well, a transistor, you say, well, shouldn't that be good enough? The amplifier, you can put in a millivolt. And yeah, well, if you put in only a millivolt, there'll be a big energy cost of amplifying the weak signals. So that's not the solution. The solution is the response to the transistor. Today, the transistors turn on and off, and there's a certain steepness. And what we really need is something that's even steeper, that it's more of a step function turn on. And it's more of a step function. It's a more sensitive transistor, and it turns on and off with a smaller voltage, hopefully in the millivolt range. So that's what's being pursued in transistors. I'll show you more about that in a minute. In cryoelectronics, yes, you lower the temperature, you lower the voltage. There are superconducting switches that are being actively investigated, but this benefit from going to low temperatures actually also occurs even if you use transistors at low temperatures. And just at low temperatures, you just get a better match of the switch to the wires, so you actually gain. What about a nanomechanical switch? So I have here a sort of an example. Think of a lever, and you have one electrostatic charge at the tip of the lever, and so it responds to an external voltage. However, suppose instead of one, I had 3 electrostatic charges. Then the response is 3 times greater, and in effect, you are more sensitive. You can put, why stop at 3? You can put 10 electrostatic charges at the tip of a little cantilever. And so the switching action gets easier and easier the more electrostatic charges you have. So you can really help yourself that way. The optical example I mentioned earlier, there are a number of ways of doing it. The key idea is you have a weak optical signal, you still get out a big voltage. However, there are problems. You need a lot of photons to get a good bit-error ratio. 10, more likely 15 photons are needed to get a decent bit-error ratio, and the light sources are not that efficient. Sometimes you have 10% efficiency, and so, yeah, sure, it works great, but then you're penalized by 2 factors of 10. Now you're 100 times worse than expected, and so maybe not optical, except for the longer reaches. The great strength of optics, it'll go a longer distance. So if you have to go a longer distance, maybe you're willing to pay the energy penalty. So so this is sort of an idea, why there's room for improvement in the optics is currently, as we currently do it, we need 10,000 photons to represent 1 bit of information. However, if we had more sensitive detectors, so it's really about detectors, even 15 photons would be enough. And so that would be almost a factor of 1,000 improvements. Even there's huge room for improvement. What about nanotransformers? Well, we don't have very many examples in technology of what is a nanotransformer. But there's one example. It's not a very practical one. But when you use wires, metallic wires at optical frequencies, you have a wire, it has sort of a normal impedance. By that I mean it's like the usual impedance, like 50 ohms, or the impedance of free space, 377 ohms. This is the typical impedance, but if you taper down to a sharp tip, you actually get a higher impedance, and the taper itself acts as a transformer. So that'd be great. Here maybe we'd insert a transistor, and it would operate at the high voltage, and then it would be, as it sort of flares out, we get the back to low voltage. But unfortunately, it only works at optical frequencies, so no one knows how to make it. Maybe one of you will figure out how to do that. There is another concept put forward by Professor Saif Salahuddin, a newcomer to our department, and it's kind of a transformer. It's using a ferroelectric gate insulator, and a very small change in voltage causes a very big change in charge. This is kind of like a load line. It's kind of a neat trick, but it needs to be delicately balanced, so it has issues. Everything has issues. What about electrochemically driven switches? Well, how many atoms of copper do you think it would take to make a short circuit? Does anyone want to guess? Anyone have a guess? Suppose you have two copper wires very close together. Maybe, would you say 1,000 atoms of copper might be enough? So I would think so. I think 1,000 atoms of copper could cause a short circuit. And so you can sort of visualize, oops, there it is. There's my short circuit in there. And that wouldn't be bad. That's what the requirement was. We needed sort of 1,000 electrons at a millivolt each. You're driving copper to copper. Maybe that will work at a low voltage. And you grow electrochemically, and you end up making a short circuit. And however, there's a little bit of a problem. It's painfully slow. And if you try to go fast, if you try to plate out the copper very, very rapidly, there's something in electrochemistry called an overvoltage, and then you lose what you gained. And so this is not quite it. This is not quite the solution, but there's a lot of research happening here. So this is the montage of all the different technology options. Actually, I didn't dwell on this, but I'll just mention it. I didn't have a slide for it, but it represents a magnetic switch. It's real. It's in every hard disk. Maybe we can use it for logic and communication too. That remains to be seen. Okay, so that sort of lays out the territory. So I have a few minutes. I'll give you my favorite solution, and that's there is a sort of a transistor type solution that I kind of like, but we'll see whether it can be made to work. And it harkens back. Actually, it goes back a long time, but an important step was taken at the Hughes Research Lab about 10 years ago. This was in 2000, and they said, "Look, we have two semiconductors." And a strange thing happens with this particular combination of semiconductors, gallium antimonide and indium arsenide. A very strange thing happens. And the strange thing that happens is, and this is unusual, is that the conduction band of the indium arsenide lines up with the valence band of the gallium antimonide. And you could create a switching action because this valence band, it's filled with electrons. And the conduction band is empty, so you could create switching action when the bands just overlap. And this could be very sharp. Now, how sharp could it be? If you take a class in electrical engineering, we normally teach as if the band edges were perfectly sharp. If they were perfectly sharp, this would be a fantastic switch. Now, we don't teach, of course, that the band edges are not perfectly sharp. They're reasonably sharp, but they're not perfectly sharp. So that's a limitation here. But it's kind of a nice idea because you adjust it in a small voltage change, and suddenly these things overlap, and suddenly the current begins to flow. And it depends not upon thermal activation, but rather upon the sharpness of the band edge. So that's kind of nice. This is a 3-terminal version of that device, and you can see here it's off. The electrons in the valence band, they can't make it. There's no energy states available. However, you change the bias a little bit with a gate, and suddenly the electrons can jump across. So this is sort of like just the threshold of turning on. So you have here the potential for a switch that is not thermally activated. That could be a very, very sudden switch. So this is on. This is just beginning to be off, and this is sharply off. And you can see the 3 bias cases, and people have worked this out. So there's actually a very large effort at Berkeley, led by Chen-Ming Hu and many other universities, to try to make this practical a lot of issues. Worst issue, the band edges are not perfectly sharp. This is roughly what that device would look like. It looks something like a transistor, but let me show you the current path. The current path is, and the important step is this vertical step where you jump from the valence band on one side to the conduction band on the other side. It kind of looks like a field effect transistor, but a normal field effect transistor would have, let's see, be N plus on both sides. Oops. N plus. And however, you see, this is different because on one side it's P plus and the other side it's N plus, and the current path, instead of going straight across like it would be in a normal field effect transistor, the critical step is sort of this upward step. But it kind of looks like a transistor, so it has a shot. You don't need to make it in a 3.5. You can make it in other things. This is a close-up again of the switching action. When you have this overlap, you can start moving electrons across. Now, there's tunneling is taking place here, but this is not about tunneling. This is about overlapping the density of states. I call it a density of states switch. This is another way of looking at it, and this harkens back to the names of PN junctions that we've known. The Zener diode, you have this kind of overlap, and once you go to sufficient reverse bias, you turn it on. Okay, that's actually used in electronics a lot. It's called a Zener diode. There's the Esaki diode. This used to be used a lot, and again, you get an overlap between conduction and valence band, and you get a step, but you get the step in the forward direction. So it's another kind of switch, not that sharp a switch. And what we're looking for now also was invented back in the 1960s. It's called a backward diode, and you have the forward diode action to turn on, but right around zero bias, you have a turn on in the reverse direction. And the turn on is just due to the beginnings of the overlap between valence band and conduction band. And these actually work reasonably well. Even as homojunctions, they work reasonably well. And they've been studied. Unfortunately, they're only a factor of 2 better than regular transistors in the form that they've been made up to now. So clearly some further improvements are needed also, although it's kind of a nice device, and it is used in radios as a mixer. This switching action is very, very helpful in radio communications. And so there it is. So let me kind of skip through this. I'm sort of running out of time, and let me jump ahead to my conclusions. So the conclusion is really that we have this. Here are your options. Maybe you have some better ideas. By all means, bring them forward. If you do come up with a better idea, first thing you do, you email me. Okay? So what are the conclusions? So, well, the conclusions, what happens is, you know, how all these things work and so on. What if you lower the voltage? Whoops. What if you lower the voltage? Maybe that's bad, but you'll never deliver the current. But I remind you, the purpose of the voltage is to charge the capacitors. If you lower the voltage by a factor of 1,000, you also require 1,000 times less current because the impedances have stayed the same. So this is sort of this means that it's probably likely to be successful. You'll need some current requirement, and the way to express this, I see I'm getting into the weeds here. This has to do with the figure of merit. I'm arguing here instead of milliamps per micron, which is a normal requirement for transistors, I'm arguing at low voltage it should be millisiemens per micron. So let's see, where are my real conclusions here? Well, I think I'm going to conclude with that slide. Okay, obviously there is a need for a lower voltage switch, and somebody is going to come up with it. There is quite a bit of research on this right now, so I can just sort of smell it. Someone's going to do this, and it's going to replace the transistor. Think about this. Inventing something that replaces the transistor, that would be quite astounding. So I'm waiting to hear what ideas you might have. Okay, so let me conclude with that. Email me first if you have a good idea, or bring it up during the question period. Okay, thank you. Okay, so let me remind you, I asked a question at the beginning to the policy wonks, and if there must be a few in here, is if you make electronics much more efficient, will the total energy use actually go down or go up? So that, anyone want to
Who knows the answer?
address that? Okay, we'll just leave it as a puzzle for now. Okay.
Do you have any questions for Eli? Is all crystal clear? Oh.
To be fair to the graduate students, they should write the idea in their notebook before they email you, I think.
Okay.
Any technical questions? Comments? Okay, well, I guess we'll conclude with that. Thank you.
Okay, thank you.